Good afternoon, ladies and gentlemen. We're ready to start our presentation. As a courtesy to others, please place all electronic devices to silent. Thank you.
I'm Clay Benziger, and I'm presenting from Bloomberg. I've been talking with you about multi-tenancy at Bloomberg, in particular how we work with HBase, and as well how Oozie is able to give us an advantage here for multi-tenancy, being able to run a lot of automated tasks for us and able to help out. Let me give you some background if you're unfamiliar with Bloomberg. I'll start with that. We'll have a technology introduction if you're unfamiliar with HBase. Try to speed as quick as we can. And thereafter, we'll work through HBase multi-tenancy and some of the workloads that might incentivize this, resources that can be challenging, and access. Thereafter, we'll walk through Oozie self-service, how you can enable, if you're an infrastructure operator like I am, your tenants to be able to actually be able to empower themselves in their applications. We'll look at deployments in particular, and then finally, how to combine HBase and Oozie. Options, exporting HBase, two of the drivers there. So with that, just a little bit of background about Bloomberg. Bloomberg is responsible for quickly and accurately delivering business and financial information. Basically, if it moves the world financial markets, we need to report on it. We need to be able to give people access to that information. Furthermore, we also have to be able to deliver the news and be able to report the news accurately to be able to help drive this financial information and the actions people want to take on it. It's cut now. With that, we appear with 550 exchange feeds, getting over 100 billion market messages every day. So these could be people offering to buy or sell an equity, all the way out to exotic derivatives and mortgage-backed securities. We process 400 million emails and 17 million IMs a day, instant messages a day. And we do that across the Bloomberg Professional Service, or the iconic Bloomberg terminal. One of the interesting things about this is that this is not your typical SMTP or XMPP messaging and mail system. This is actually a system by which people execute financial trades. So it's a very different level of service than, say, your typical email provider. And then with that, we have the 2,700 journalists and analysts who actually work in 120 different countries, provide us all of this content. So 5,000 and reaching over 360 million homes worldwide. With that, we're also a technical company. We have and to a variety of Apache projects, filing JIRAs, as well as even taking PMC roles in Apache Solar. We have 3 committers, 1 a PMC member. We try to be very broad-based in our infrastructure and our support of trying to make the infrastructure as resilient as possible. So with that, you can see that we've got JIRAs and commits into things ranging from incubating Apache Hawk all the way to quite a bit of extensive work on HBase and Phoenix. So let me walk you through kind of the technology we'll be discussing today, the HBase and Oozie that actually underpin this talk. So if you're unfamiliar with Apache HBase, it's a distributed database. It's based on scaling out to very large tables. Billions of rows, millions of columns, and being able to do this for sparse data as well. So it doesn't have to be dense data. That said, it still has very good block caching primitives, the ability to work with Bloom filters and other sorts of index optimizations to try to be able to look up data very efficiently. And then it provides timeline consistency as well for high availability. So with that, we can actually make it very advantageous for real-time queries. Similarly, the way it actually partitions this data out is by sharding. It maintains versions, and it's a non-relational database model. So it does follow Google's Big Table paper. Thank you. Test. So one of the key drivers for some of our Oozie work and our backup work is actually the fact that this relies on a log-structured merge tree. So if you're unfamiliar with a log-structured merge tree, just to kind of give some motivation on how some of the later slides will work, of course, we're all familiar with HDFS and the fact that HDFS is largely an append-only file system. So if you want to update data in a database such as HBase, you have to write new data. But this means that you still have your old data running around. And how does that work? So HBase is designed in such a way, following the big table model, that it's actually able to write new data and ignore the older data until it's convenient to delete that older data. And it does what's called a compaction. So furthermore, because of that model, it's actually able to support some very neat stuff for exports and backups. But one challenge is, because of the infrastructure impact of that, this can only be done by global administrators in the permissioning model of HBase. And this kind of hurts our self-service. So we use also Apache Oozie. And if you're unfamiliar with Apache Oozie, it's a scheduler for the entire Hadoop ecosystem, really is its kind of goal, to be able to schedule across a system in a distributed acyclic graph, which means that you start at one point, you work your way through the graph without looping ever, and you come to the final conclusion of what your workflow is intending to do. Workflows can be templated. This is a really powerful thing. So say you have a development cluster and you have a production cluster. You want to run the same job in dev as you run in prod usually to make sure that, hey, you know, everything works. I can roll it out to prod and I know it'll all work. But the host names might be different. Database names might be different. So the templating is a really powerful feature here to be able to actually allow you to just change out the configuration, if you will, and run the exact same code. Furthermore, Oozie provides a coordination service. So you can kind of think of it as a distributed cron, if you wish, in the sense that you can actually schedule jobs to be run either by time or by data availability. So if you have another team or another product that's delivering data to your HDFS, Oozie will kick off when that data arrives, and then it can run that regularly as well. Now, one of the very big advantages for us in working with HBase is that Oozie is integrated with the rest of the Hadoop stack. So it supports several types of Hadoop jobs. You can run a pig job, for example, or a Hive job, a Spark job, MapReduce job, a Scoop job, goes on. Furthermore, it has logic constructs. So if you want to branch in your workflow and rejoin, it supports that as well. And all of these are provided out of the box. Overall, Oozie aims to be a scalable, highly available, and extensible system. It's based on the Tomcat web container service. So moving right along, let's try to understand kind of HBase multitenancy and what some of the challenges are there and why anyone would want to do that. So for us, we have tens of tenant teams that run on our infrastructure. And one of the biggest challenges for us is a larger capacity reserve. Financial markets are not level from day to day. They can have spikes in them. And with that, we have to really be prepared for these capacity demands. But it may not be across the entire ecosystem that we support. It may just be one product here or one product there. And it doesn't make sense to scale out each of those products to support their maximal spike. So multi-tenancy provides us a very big ability for that reserve there. But furthermore, it also is key for capacity. All of our clusters, you know, if you're running a Hadoop cluster, it should hopefully have topology awareness. It should know that some machines are in one rack and some machines are in another rack. If that rack goes down, if that's a three rack cluster, for example, you just lost a third of your capacity. That's a pretty big impact for any of us. But if that's a 30 rack cluster, well, I lost 1/30th of my capacity. I'm not probably going to notice terribly much. And if that's a 300 rack cluster, I really probably don't care. So the scale at being able to lose a rack is really key for this multi-tenancy and to really provide a resilient environment. But with that, we get higher per machine usage, hopefully. We can drive our entire system up to be utilized more and still have the reserve capacity to satisfy any spikes. And then also, there's still some challenges. Multi-cluster Hadoop has been around a long time, but it's still evolving. So this can be delegation tokens or how you actually authenticate to a peer cluster when you're on one cluster. This can be querying multiple HBases from Spark. All of these things are evolving, and they're getting a better story about them, but right now building a larger Hadoop cluster is often easier than building many separate Hadoop clusters. There's definitely some arguments on why not to do multi-tenancy, just to kind of cover those. You can't get better isolation than just saying, hey, those folks are running on a different system than me. You know, unless physics fails, they aren't going to affect me because it's completely different computers. And it's easier to understand, frankly. You get emergent behavior in our distributed systems, and with a multi-tenant system, you have more effects in that system that you have to rationalize about. So these are challenges. That said, I think they're pretty tractable, so let's move on. So with that, HBase supports a number of workloads for us, and I think pretty much any HBase workload can largely fit into these constructs where you either have a write-heavy workload, a read-heavy, or a mixed read-write workload. And each of these have attributes to them that really kind of dictate how you want to tune your region servers. You can have Memstore-heavy configurations in a write-heavy cluster so that you can bulk more data up as it's being written and flushing it out to disk, trying to be able to keep the buffers able to continue to receive data without having to block. You can try to optimize your compactions for H file size, so this way that you can have more efficient flushes to disk. Again, you don't have queues backing up waiting to flush data. And you can actually tune your flush sizes in HBase now. So with in-memory compaction in HBase and things like that, if I have row keys that are changing very rapidly, I can hold them in my Memstore and intentionally not flush them. And I can flush more static data out that I don't have to keep updating. So there's a lot of options that we can do for these tunings here that really help out in a multi-tenant environment to try to provide this, this reliability. Similarly, for a read-heavy HBase, you can have a cache-heavy cluster. You can take off-heap cache now into the tens or hundreds of gigabytes and be able to try to hold as much memory, much data as you can in memory. And this tends to help out significantly in these read-heavy workloads. It definitely still is a problem because it's cache, so you can always thrash that cache. Compactions are optimized for minimal H files often in a read-heavy cluster, though. The other one we're trying to optimize for being able to bulk these H files out, but we may not care about compacting them particularly much. In a read-heavy workload, we want to minimize the number of H files so we don't have to open all of the index blocks that tell us what's in that H file. If I have 20 or 40 H files for a region, and I'm looking to see if there's a region row key in those regions, I have to open each of those files and verify that. And so this is a problem. Furthermore, read replicas, feature that we've been very heavily involved with at Bloomberg. It's very helpful to have region servers that have data, so if another region server goes down, you can continue to read that data. This was something originally not core to HBase. HBase was strictly consistent. This is what we call timeline consistency. So one region server acts as a primary and it ingests all the data, but then it replicates that data to other region servers. And in doing that replication, should the primary region server go down, you still have this replica to read from. And furthermore, for standing that region back up and electing a new primary, you have machines that have hot cache and you have machines that already have some of that region data in memory so that you can actually more quickly open that region. With that, there's also the mixed read-write case, and this is one of the more painful cases because now you have to kind of balance these two tunings. With that, though, you often will find different hardware can be helpful. So if you're running on HDDs still, you have a bounded number of I/O operations that's relatively small. A couple hundred I/O operations per second is what one can usually expect out of a hard disk. But with SSDs now, we can get easily into the thousands of I/O operations per second. So this allows us to both be doing reads and writes to a disk at the same time. This really helps out so that your HDFS can scale for you. And again, those read replicas can be useful. In this case, my primary might be tuned for being able to do all of the ingest work, while my read replicas can actually be doing the data serving and the bulk of my, my request processing. So with that, let's talk about some of the contested resources a little more deeply here. In an HBase cluster, we want to make sure the darn thing's available. If it goes down, it's not helping anyone. So with that, there's about 3 major categories of bugs we'll talk about today that can bring down an HBase. And without that availability, it's not an effective HBase. Similarly, storage is very key. If we can't write data, if we can't read data, we don't have much of a database. So with that, we'll talk about three qualities there that are very key. And lastly, the input and the output. If we can't get data in or out, it's effectively just unavailable or the storage is busted. So let's understand kind of some of the tunings there that we should be paying attention to. So the data bugs that are worth looking at are things like if you've got a region that's toxic. For those of you who've operated HBase for a while, perhaps you've seen this before. Perhaps you had some sort of H-file failure on your HDFS, and you go to assign that file to the region server. The region server, you know, it's gung-ho, I'm going to open that file, and no, it somehow crashes that region server. That's fine, HBase is resilient. It will assign that region somewhere else in the cluster. Region server's gung-ho, it's going to open that file, and it crashes too. This works really well, but I only have a finite number of region servers, and this region seems to be pretty deterministic that it just keeps crashing those region servers. I've crashed my entire HBase. This is really terrible. So how can we try to prevent against that? And this is what Francis was talking about just this last talk. We can actually use region server groups. It's been committed into HBase now. It's certainly incubating well with users, you know, as Francis has been running it for a number of years. But now we can actually say, hey, which tenant is causing this failure? You know, it's sometimes a little bit of a hard thing to figure out from a Java process that just crashed, what caused it to crash. I can look at the stack, but what was the data that caused it to crash? So now I can start partitioning my users out. I can do a binary search if it's, you know, unfortunately just a true needle in a haystack, and start partitioning my cluster up until I figure out which half is crashing, and continue to drill down until I've figured out the pernicious user And now I can work with them to try to fix their data. Similarly, HBase and all of our distributed systems in Java and multi-threaded distributed systems in general have a challenge of thread death or starvation of resources. So if the master becomes a zombie, I filed this Jira, so I like it, I guess. If you lose HDFS, the master would lose its thread for HDFS, and it would never reconnect. This is an interesting challenge that came about in the HBase 1.1 era. But if your HDFS has gone down hard, HBase master says, hey, you know what, I'm alive, I'm still gonna heartbeat into Zookeeper, that's perfectly fine, but it loses its HDFS thread. Now HDFS comes back and, hey, we're in business. The HBase master's still alive, that's fantastic, except for nothing's happening because it can't write to HDFS. This is a very kind of good example of thread death. There's a number of different bugs throughout our ecosystem that can cause this, but it's something worth looking at. Region server too busy is a great one. I'm sorry, I'm just too busy. Region server, you'll have to try again later. But this happens when your queues are full. So, it's got to turn you away. It's admissions management. So we've got to deal with that. Similarly, garbage collection bombs. This was an interesting failure for us again, where somebody was writing very large requests as a multi-put to us, and they would actually manage to run us out of garbage collection ability, basically. They'd write more data and create more objects faster than we could garbage collect them. And we'd end up crashing our region server. But again, kind of like a thread death situation, figuring out what just happened. What data caused that? So at least this way we can try to start emitting log messages saying, hey, I just took on a multi-put that wants to write 50,000 rows in one request. Maybe that's a little suspicious. Maybe you should go follow up with that client and figure out what they're trying to do. So these are kind of some of the things coming into the ecosystem or in the ecosystem now to mitigate some of these challenges. My apologies, I forgot to mention for region server too busy, we can actually use a neat feature now called request quotas. So you can actually limit the RPCs that a user is providing you. So if users say, you've told them, hey, look, my SLA is you can write 500 queries a second against me, or you can put 500 rows, 500 put requests against me a second, and they try to do 501, they get an exception. Please try again in a second. You've maxed your quota, and that's the end of that. So these are useful hardline features there for trying to mitigate against that region server too busy for all tenants. Similarly, users are always fun when you're an infrastructure operator because they're very smart. You like working with them, except for the fact that they crash your systems. So coprocessors are fantastic in HBase. There's definitely a lot of warnings in the community that they can be dangerous. There's Apache Phoenix, which is effectively a beautiful set of coprocessors. We certainly like running Apache Phoenix, but one of the challenges is, how do you run this really nice curated set of coprocessors that are an Apache project and make sure that a very ambitious developer on a product team doesn't also try to deploy some untested coprocessor? And traditionally, there wasn't a way to do that. There's some good heuristics presented at HBaseCon East, if you want to follow up on the slides there, for how to try to go about writing a coprocessor that hopefully doesn't take down your cluster. But if you want to just say, hey, you know what? I like Phoenix, or I like some coprocessor that I deploy today and I don't want any others, you can also whitelist coprocessors now. So you can say, hey, these are the coprocessors I trust. This file path on HDFS or this file path on all the region servers is safe. Anything else, reject. So this helps out, again, just to provide that level of isolation and stability. With that, let's talk about storage. So storage is a very key resource for us. We've got to be able to write and read our data. So here we've got Memstores, which are our first kind of memory tier in HBase. When you want to write data, you write it into the Memstore. If that data's hot, you can actually serve it right back out of the Memstore. And this is really, hey, caches, we like them. The problem is it also affects the H-file quantity. So if you say have 1,000 different regions on this one region server, kind of more than usually is a good heuristic, and they're all doing ingest, you're going to keep writing really, really small H files from this region server because we have to dump that Memstore. We can only fill up so much data. We got to write it to disk. And this is going to make life very difficult for us when we try to do that compaction because we've got that log structured merge tree. We have to take all those H files. We've got to make them one eventually per region, or at least try to lessen the cardinality to some extent. One other challenge with the Memstore, if we're writing more data than we can flush quickly, just blocks writes. Sorry, can't write right now. I don't have anything to write it in, so I can't accept your write. So we have to be very mindful and monitor well that Memstore. Very cool feature coming about the compacting Memstore. So you can use this, like I said, to be able to actually hold fast changing data in the Memstore and just continually hold it there and write the slower evolving data out to H files. Next, we've got HDFS. HDFS is tried and true for quite a number of years. One of the challenges is traditionally there's no way to stop HBase from filling it up. You can set an HDFS quota on your HBase directory, and that's fantastic, but it just causes your entire HBase cluster to crash when you fill up your HDFS or hit that quota. So this isn't a great experience for a multi-tenant HBase. You know, one tenant goes rogue, they fill up your HBase, and everyone's now just sitting in the dark. So with that, HBase 16961 is introducing a file system quota semantic. So you can actually say, hey, you know what, this table gets this much space, or this namespace gets this much space. And here's how you should deal with that out of space issue. You should either disable the table, or you should just set it into read-only mode. These are some of the heuristics being talked about here. And hopefully, I think this should help a lot of folks in multi-tenant situations if you're especially tight on HDFS. Next, multiple workloads thrashing in the cache. There's not a great, you know, caches are hard in this regard, right? There's admission control policies. We have eviction control policies. HBase has some work going around a neat algorithm called tiny LFU, tiny least frequently used. It's a new admissions control policy, and we'll see. Maybe that can help us with some of this cache thrashing. But in the meantime, the best thing you can do is really look at your cache hit ratios. You can see these in JMX and actually understand, am I using my cache efficiently? Or do I have these huge off-heap caches and is nothing still getting served out of my cache somehow? So at least we can get some visibility into that and then try to start kind of reverse engineering what's going on with our caches. And with that, let's talk about some of the monitoring here. So this slide, we've got some talk about the input and the output of HBase. Again, if we can't get data in and out, even if we can store data and we're available, well, if we can't get data in and out, we aren't much available or really storing anything worth storing. So with that, there's a challenge here with caching. We've got to be able to store that off heap. This helps out a ton to lessen our garbage collection times. So if you're trying to do garbage collection on more than 32 gigs of RAM, it takes a while. It's very hard to tune. It's very hard to get deterministic short performance out of that GC. So if we just simply off-heap that memory and we go back to a model where we deterministically manage the memory, it works out much better, and HBase supports that well. So it's a very good feature to use. Another one is deprioritizing scanners. A lot of workloads may use scanners. MapReduce jobs tend to like to use scanners. You might have scanners in there as a way to back up data because of the requirement for an administrator to do an export of a snapshot today, or an administrator to do a incremental backup. So you may just simply do a MapReduce job that scans. Again, for the caches, this is terrible for caches because we're now thrashing them. Be aware, you can actually turn off the cache use from a scanner so that any data in your scan will not hit the cache. And this way, your individual gets that actually can benefit from that cache much more likely can still be able to be hot in the cache. You can also deprioritize those scanners so that they don't actually take all the resources away from those gets that might be more interactive jobs. This is a new feature in HBase that's very helpful. Let's also talk about queues. HBase has a number of queues to try to do admissions control and just kind of as the data weaves through HBase, the region server. We've got our replication queue for trying to replicate data to other HBase clusters, as well as the handler queue itself, which is what serves responses. And here we've got a graph of a cluster, just with looking around at our clusters today, to see what fun pathologies could be found. And this particular graph just tells us we had a relatively big compaction event. We had 579 compaction requests in the queue, I guess a couple days ago. But we also see here this metric on the right side, and yes, we've got the 75th percentile of the max time for a get. And that looked pretty painful there. And it didn't recover for almost the majority of the day. As that compaction queue was eaten through, as the cache was then cleaned up, data locality probably was impacted, et cetera. So you've got to make sure that you've got a way to be able to actually view these metrics. And these are all just from JMX metrics that HBase emits. You can get that by going to your region servers or your HBase master, even with a web browser, and just go to /JMX. It'll dump you a bunch of JSON. Or you can use a true dedicated JMX client and try to pull that routinely at regular intervals. But this is really helpful to be able to do postmortems of what did just happen to my HBase cluster. It's down now, but how did it get down? You know, what killed it? Or furthermore, hey, things were slow last Tuesday. What happened? Well, I don't know. Did you run major compact on one of your tables? Oh, yeah. Well, that's what happened. So with that, it's very useful to have these metrics, and you've got to pick a good metric system that works for you. We also have ingest. We've got to think about how that affects things. So we've been talking about compactions, but splits are also a problem. So we've got this log-structured merge tree. And we've got regions of a fixed size. You know, we've got a start key and an end key, but we keep putting more data in there. And if that data is dense, it keeps expanding those regions. At some point, those regions get too large, and we have to split them. It becomes two regions. Well, that splitting is a somewhat time-consuming and I/O-consuming effect. And furthermore, it may even have network effects if we end up then putting that split region on a different region server shortly thereafter. Now we've got to close the region and reopen it somewhere else on the network. So it's very key to actually watch these things and be able to plan them. Same thing for compactions. You might have a system that gets a lot of data ingested during the day, but at night it's relatively quiet, or maybe on the weekends it's relatively quiet. And if you can wait and push out your compactions until that quiet time, you don't impact your daily reads as much. So it's very key to actually watch all of that. And lastly, bulk loads. Don't forget HBase can be bulk loaded into. You can use a Spark job or a MapReduce job and batch all of your data up, maybe every 5 minutes. And instead of actually talking through the front door of HBase, hey, here's a big multi-put with 50,000 requests, you can instead say, hey, there's 5 gigabytes of data over in HDFS. That's all written out as H files for you. Just go ahead and open it like a new region. And you don't have to actually worry about those queues. You don't have to worry about the compactions and the splits nearly as much. Let's talk about accessing HBase, because if you've got a multi-tenant HBase, you probably want to know who's accessing your HBase. It's really key to understand, hey, application A just used 95% of my cluster's capacity for requests for the last hour. And application B is currently at my desk yelling, why can't they use HBase? So with that, we've got a couple things that we've done that have been very helpful for us. We use LDAP. It's a pretty standard thing. I think probably most folks in this room have access to an LDAP server, maybe a Microsoft Active Directory or an Open LDAP or a DS389 server that serves your organizational hierarchy. Hey, my login name is this. My full username is, my first and last name is this. With that, we also have groups in LDAP, which is really nice. So you can see project A is in this group, project B is in that group. And one of the challenges is those groups might be hierarchical. So with that, we said, hey, it'd be really nice to traverse it and look into group A and see that group A is composed of group J and K. And with that, then those resolve to users, Bob and Larry and Sarah. So this works really well. One thing to be very cautious of, when you start traversing LDAP, that could potentially put a lot of load on your LDAP. It is a database too. So try to limit that. The patch that we've got here, Hadoop 12.291, lets you set how deep you want to recurse. We run it at 1. We'll look one group down, but if it's more than that, you're playing fast and loose. So we're gonna stand back and say no. Similarly, namespaces are very helpful. It's very helpful to be able to, with the space quota work that's evolving, with the region server groups that's evolving, to be able to say, hey, Group A is all of these tables and make an HBase namespace out of it. You can do privilege isolation that way. You can say, hey, the folks on Group A are administrators of namespace A. People in Group B are administrators of namespace Group B, but no one's a global administrator. No one can maybe run a major compaction anymore. Folks can't accidentally affect one another's projects by accidentally just doing a disable on a table. And with that, then there's the grant syntax. It's very much kind of like any SQL database that you might be familiar with regards to grant syntax, to be able to actually permit people to read or write data or execute coprocessors for that matter. Back to this issue, those multi-clusters as well. So we try to run a multi-tenant system, but we still have many clusters, as I'm sure many large organizations tend to have. And with that, there's some work here that's working very well. The Spark HBase connector out there under Hortonworks Spark on GitHub now has a feature, pull request 120 I think has been merged, that allows you to talk to multiple HBases from Spark. So if you want to try to do kind of a poor man's join, or if you want to try to do reconciliation between 2 or 3 or multiple different data centers, you can finally try to do that. I know those folks would definitely love some feedback on it, but this allows you to start to actually talk to multiple clusters. Similarly, Oozie delegations. So there's actually work in Oozie that's been committed to be able to allow you to do kind of an HBase table copy between 2 different HDFSs, whereby you can have delegation tokens, as they're called, the credential that says you are who you are on the HBase cluster, in Oozie for 2 different clusters simultaneously. So Oozie 1646 there. Let's continue to move along here to Oozie self-service. One of the key parts about Oozie that I really like is the fact that it is kind of an automated cron. It's just out there. It's doing stuff for me. I don't have to think about it. And if things do fail, it has a pretty nice framework to get job status so that we can alarm on it. And with that self-service, let's kind of think back real quick. Self-service, yes, it's the serving of oneself with goods or services. Well, if I'm an infrastructure operator, every time my tenants can serve themselves, that means I can go develop the next product. I can do, make their system more reliable. It's a very helpful thing for me. So I really want everything to be as self-service as possible. If I have to approve a request or if I have to log on and do anything for them, it's a failure of me to be able to actually enable my tenants to be able to be better developers and to get their applications out the door. So with that, Oozie provides me this automation ability. I can have pipelines, the workflow construct from Oozie. I can similarly have reoccurrence of a job. You know, every Saturday I need to do an HBase major compaction. Cool. Well, I'll schedule that. I don't want to wake up on Saturdays. I like sleeping on the weekends. So with that, you know, the reoccurrence is very helpful. The job status that Oozie provides, it can do a couple different things, but one of the ones that I like is callback URLs. So I can run a nice little web service that Oozie will call and tell me, hey, this job died. You might care about it. You know, similarly, it might say, hey, this job succeeded. And I can look at that and say, hey, great, tick the box, just make sure that we know that we did that and all looked well. But it's really nice to be able to actually set these pipelines up for automation and alarming. Job IDs, Oozie is really nice as well because you start submitting these jobs and you go, hey, you know, I just need to run a Spark job for each HBase I operate. That's great. A couple hundred you know, Spark jobs later, I really don't want to try to do that bookkeeping, and Oozie does it for me. So it tells me, hey, on this yarn cluster, here are all of your application IDs, here's the success or the failure of each of those jobs. Similarly, it does authentication. So this is a very big part, again, for the tenant self-service. If you have a Kerberized infrastructure and you want to access the cluster, you either need a login and password, which is great when you're a human, but terrible if you happen to be an automated process because they just don't have hands and keyboards don't work real well with them. So instead, you have to use a key tab. And that key tab's kind of a challenge as well because now anyone can have that key tab. I can always just CP it and hand it to somebody else on my team and, hey, look, we're all this role account or we're all this account. And that's kind of a moral hazard. With this, the Hadoop ecosystem has a very nice tool called a delegation token. It's something local to that Hadoop cluster. It means that we don't have to use the Kerberos infrastructure and really beat it up when we have 1,000 node clusters requesting Kerberos tickets. We just do one request to Kerberos, and thereafter we handle all internally with a delegation token. Oozie, as it's normally deployed, is a proxy user, as it's called. This proxy user can impersonate people on the Hadoop cluster. It can write a delegation token for anyone it's permitted to write one for, often everyone on that cluster. It's a dangerous thing, be aware of that. Your Oozie could be a way to own your cluster, could be a way to break into your cluster. But that said as well, it's also a fantastic resource for being able to make self-service applications very easily without having to write a bespoke application, which maybe doesn't have as much security review. So these delegation tokens means your tenant teams don't have to use key tabs. They might use their login and password to authenticate to Oozie, and thereafter, Oozie will say, hey, I verified that the person who submitted this was legitimate. As long as you got faith in me, we're good. And thereafter, it uses the delegation tokens. So one of the key things for me is how do tenants, ideally without a key tab, deploy their software? This way, I don't have to worry about them logging onto prod as their role account that I think is running vetted code that's checked into version control. I just, hey, they check that code into version control. That's what should be deployed on the production cluster, and it's running. So with that, some JIRAs that are working through the community right now, Oozie 2877 provides a Git action. The same way that there's a pig action and a hive action, well, let's make Git a first-class primitive of Oozie so that I can actually get code onto my Hadoop cluster instead of it magically appearing there. Because for hundreds of people, it apparently just doesn't magically appear there. They actually do a lot of work to get it there. Similarly, this does require, if we want to deploy code to a Hadoop cluster, for those of you who are familiar with configuration management, such as Chef, Puppet, Ansible, CF Engine, and Salt, et cetera, there's some axioms we need to follow. Because unfortunately, Oozie is not a configuration management language. And none of those configuration management languages are terribly aware about cluster primitives either. So we have to think about some stuff that comes from that discipline and that software engineering world. So we have to think about when we deploy our software now, it needs to be idempotent. On reruns, because maybe we're deploying Oozie, deploying jobs through Oozie out of a coordinator. So every Thursday it wakes up and says, hey, I'm going to deploy the latest application. We better make sure that it probably does the exact same thing it did the time before as far as how does it start that application? How does it copy things to HDFS? Are we getting an infinite stream of files? So, you know, maybe it's not every Thursday, but it's every 5 minutes on the hour it runs. And maybe every 5 minutes on the hour it makes 1,000 files. Sounds like it's going to be a really bad time in about a year when I go, why do I have all these files on my HDFS? And they're all small files. My name node's crashing and I have nothing on this HDFS. So we have to think about that. Similarly, cleanliness. As the software evolves, how do we pull the old versions off? Sadly, we don't have primitives for that. We can talk to our source code management system and pull the new versions down, but this is still left as an exercise to the reader. The last part is, I think, probably something, again, the templating in Oozie encourages this, but we need to separate configuration from code. We need to make sure that we write this deployment workflow so that it runs on our development environments, and the developers should have full access there. They can go, yeah, this works great, or it doesn't, and then go, yeah, it works great. And once they say that, they can roll it out to prod, and they just simply put in the bits for it to work into prod. So key thing to kind of think about, these are some axioms to ponder. Some great source to kind of come up with this methodology, if it's new to you, is a website called 12-Factor App Design. Sorry, I didn't make the slide, but you can also find the cluster continuous delivery with Oozie from ApacheCon a couple weeks ago, where there's some more thought in this and how one can architect it. So let's now talk about the meat of the material here, HBase and Oozie. How do we actually integrate these two things, and what can we get out of it? So again, the self-service, no DBA. I think probably a lot of us have either come from that discipline or have been software engineers who've worked with DBAs where it was just a very frictionful relationship. Ideally, we can get away from that, so that's probably better for everyone. We can make it regularly schedulable. Again, HBase itself is a great database, but there's no way to poke it reliably, but that's what Oozie does very well. Key thing is it runs as the project user with no key tab. So HBase itself tends to be a little more hard for trying to get delegation tokens. Sometimes you can't renew them like you can for much of the ecosystem. You have to just get a new one when it expires. Oozie is able to do that for us. And then logs and reporting. HBase as well, there's a number of exceptions that can sometimes crop up. Maybe, hey, I was just too busy and the region server told me to jump in a lake. But at least Oozie is very good at reporting those logs and recording and giving us an audit trail. Similarly, we can report the success of a job with those proactive callbacks. So again, if we've got a read-heavy system that's critical for our application or our company, we can get verification that everything's running healthily. And we can verify the performance of the jobs with Oozie has a service level agreement subsystem, an SLA subsystem that one can actually run through and be able to say, hey, I expect this job to run in these times, so I can get the feedback that is that job running in that time, or did it go out to lunch and it's been running for hours upon hours on end. And lastly, just kind of that infrastructure insight. As an infrastructure operator, if you've got it to the point that everything's self-service, you have no clue what's running on your cluster, and you're blissfully happy you have no clue that's what's running on your cluster. But sometimes somebody comes to you and says, your cluster broke. And kind of your first question, because we're all human, right, is probably, well, what did you change last? And sometimes that happens, sometimes your cluster broke. But the key thing is at least Oozie gives us a really nice audit trail to be able to say, well, what is running on my cluster and when did it last change? So let's get to the meat of the scheduled compactions. So HBase scheduling compactions is kind of one of those HBase 101 things for a lot of folks who operate read-heavy and write clusters. But compactions are I/O and processing heavy. And with that, they can be detrimental to our read performance. They can be detrimental to our write performance. Well, that just made a pretty bad database. And they can also lead to split storms and rebalancing. So again, we want to probably have very intense monitoring and maybe a little bit of time for that if we're really having heavy compactions. And it's good to plan for that impact. So let's schedule them for a time that works well. Now, one of the kind of nice things is the HBase API, we can actually go region by region. As a human, I'd never want to do that on some of the 30,000 region clusters I've got. But at the same time, Oozie could certainly do that, or a Java, I should say some Java code could do that relatively well. And this way I can kind of lessen the roll-on to that impact. And if I see that I'm affecting service level agreements, well, dial it down, compact more slowly. So we can also poll to know when compaction is complete. Just a simple Java action to get folks started. It seems like this has been kind of difficult for some of the HBase developers I work with. tinyurl.com/oozie-hbase-compaction. It's just a little toy Java application that does a compaction on an arbitrary table, extend at will, but hopefully it can help you get started. And the next part is just kind of understanding what's necessary for Oozie to have the Java action load up the proper configuration. So Oozie itself writes a job conf, the same way you'd have like a MapReduce job conf in the older MapReduce framework. Oozie writes that out. We need to load that in so we know what HBase cluster we're talking to. We need to know that, where's the zookeeper quorum. Luckily, Oozie handles that for us in the workflow, but this is how it's bridged. We need to add that file to our configuration object. Similarly, we have to look for that delegation token I was talking about. Oozie hands that off as an environment variable pointing to a file. So we need to actually look at the file path and make it all work. And then lastly, we need to set Oozie's credentials action authentication. So this is actually where we do tell it which HBase cluster to go get a delegation token from. Is it using Kerberos or not and all that. Unfortunately, I can't figure out how to use job XML with that. It seems like it is an XSD issue that they don't actually have support for it. So there's an Oozie issue if you've hit that and you want to say, yes, I can't do that either, or let me know that I'm just looking in the wrong place. Lastly, snapshot exporting. With that, this requires an administrator today, but it's great because we can do a snapshot, which is a live backup, and it's a relatively consistent backup of that. We can make it self-service because you can be a namespace administrator and you can do a snapshot. We can make it automatable. Oozie can kind of the same process, call in and do those snapshots. It works on a secure cluster. But we can't read /HBase. So if I want to take that data with me to another cluster, I have to get that data out somehow, and that's where I'd have to do a MapReduce job to scan it out. And that, again, is going to thrash my caches or otherwise take resources away from whatever I'm using HBase productively for. Similarly, that backup location may not be running HBase, it may not even be running MapReduce. It might be Amazon S3, or it might be HDFS. So let's see if we can actually, without a significant architectural baggage to HBase, add in this authentication system whereby a normal user can do that. And this is somewhat an exercise of the reader and something that we've been playing around with. Hopefully we'll be able to release it, but I kind of want to see if people just throw tomatoes at me as well. The thought is that as a namespace administrator, I want to do a snapshot. I can make a snapshot, that's great, that works today. And then I want to submit an Oozie workflow as that namespace administrator. That Oozie workflow here would have an actual Oozie action, so it binds all of the kind of scary stuff that runs as the HBase user, as a global administrator of some sort, and sets that boundary to then actually be able to create a Dropbox directory as the namespace administrator on HDFS, the reverse of a HBase bulk load, if you will. So this directory will be opaque. You won't be able to CD through the directory unless you know the name of it. And it will have an obscure name, so it is sadly, but okay probably, security by obscurity for that temporary moment. And then we can export the snapshot. And this has to run as HBase or as an HBase super user. And then we just write that exported snapshot to the user directory we created. So with that, I think I am out of time. And if you've got questions, I'll be somewhere around here. Thank you.